In the previous video, we studied transportation problem. Now we are going to continue by two problems similar to transportation problems, but there are some differences also. As we can see, the tableau that we created here is almost the same. Only the right-hand side, these blue parts, or the row and columns, supplies and demands, instead of SIs and DJs that we have different values, now we have all ones. It means that instead of selecting some value from source 1 to destination 1 plus some from another source from destination 1, we are going to assign one source to one destination or one destination to one source. So we are not going to receive different values. It means that if we consider xij as decision variable, previously we said that xij means the amount of commodity we send from source I to destination j, or row I to column j. But now we are assigning them, so the value for xij has another meaning. If xij is 1, it means that source I is assigned to destination j. Otherwise it is 0. So writing the constraints for the problem also, we are going to have the previously row constraint and column constraint, or we name those constraints as supply constraints and constraints for the demands. Now we are going to have one more constraint that shows that xij can be 0 or 1, or solving with solver we will have the constraint named binary. So we are going to select all the variables and say all of them are binary variables, so they can gain the value of 0 or 1. Now let's look at the problem. We have 4 power plants and there are 4 cities, but we want to decide or assign each power plant to one city based on the cost mentioned in this tableau. So we want to do this assignment problem with minimum cost. For example, if I assign power plant A to the city Atlanta, it seems that it's going to be with the minimum cost if I have only one decision or one city to be decided. But if we have 2 power plants, for example, or looking at the 2 rows, plant A and plant B, in plant A we can see that the minimum is for Atlanta. For plant B also the same, so which one should we decide? If I assign plant B to Atlanta, which is 70, much less than that 90, but for the first row then I cannot select that cell because it's in each column we can have only a 1 and the rest are going to be equal to 0. Then I cannot select that 90 or that assignment by the cost 90. What is the next after that? 160. So I can have 70 plus 160 if I have only 2 power plants. Or if I select 90 or plant A for Atlanta, and then for plant B I have the next minimum after 70 is going to be 100. So this time I had 100 and previous time we had 70 plus 160. Now I have 90 and 100. Here also in the green part you can see the solution. After solving the problem we will see that the same thing will happen. But for 2, 3 or 4 assignments it may work. We can do the brute force way or solution, find all possible cases that we assign 4 rows to 4 columns, or all possible cases that we can have a 1 in each row and each column, and then find the total cost for each assignment, and between them we can say that this is the best solution. But when the number of rows and columns increases, then it's not going to be applicable. Again, here to the right we can see the sum for supply and demand. If the problem is balanced, so we'll continue like this one. Otherwise, we need a dummy row or dummy column. So usually, or we imagine we have one more city or one more plant, then we need to add a dummy or imaginary city or imaginary power plant. By those four that we want to find the minimum cost assignment, we will do the same for the dummy row or the dummy column. We will consider again the cost coefficient 0 because it is just to make the problem balanced and there will be no cost for us based on that assignment. And the linear programming model for the problem also is clear because after assigning these values or xij, zeros and ones for xij, we are going to have some xij1 and the rest 0. What's the total cost? So for each assignment we have the cost there. If I assign, for example, plant A to city Atlanta, then it's going to be the cost 90 for us. Then I need to add this 90 by another 100. For example, in this case, in this green part, we can say that if this is the solution, if we do this assignment, we consider this assignment for this problem, then the total cost is going to be the cost for corresponding cells for these places. For example, it's going to be this 90 plus 100 based on this one. In third row, I need to consider this 140 plus in the fourth row this 120. And the sum of all these values is 450. So we want to minimize the cost of multiplying Cij by Xij. Xij equal to 1, it means that we did this assignment, so that cost is there. Otherwise, there's no cost because if we assign A to Atlanta by this 90, for the other cities, there's no cost for this plant. That's all. What are the constraints? So again, we have similar to transportation constraints for rows and columns. This sum Xij equal to 1 says that in each row, we are going to have only a 1 and the rest zeros. In the columns, the same. However, if we don't write the last constraint here, Xij are zeros or ones, then I may have 1/2 plus 1/2. But I cannot write 1/2 plus 1/2 because when we say assignment, it means that each plant totally assigned to a city, not half to this and the rest to the other city. And this is the difference between transportation and assignment up to this point. And for the columns also, each city is going to be assigned to a plant. And Xij equal 0 or 1, which is the binary conditions, or 0, 1. Sometimes we call this type of problem 0-1 programming problem. Now, so what did we do first? By the given problem, this 210, 90, 180, we wrote them all inside this tableau. This column and that row are all ones. It means that if I consider Xij here 0 or 1, the sum for row must be equal to 1 because I want to bring those ones here to the right hand side of these constraints. Constraints are all equality because the problem is balanced. Now, let's start again and solve the problem. So imagine we have nothing here. So that's the problem. So exactly the same number of the given cost coefficients, we select some cells to save the value of our decision variables. And I named it variables, this green part. So this one is exactly x11, x12, row 1, column 2, x13. For example, this one, third row, third column, this is x33. Let's see whether it's going to be 0 or 1. Now, here inside this part, we do nothing. We are just going to select this, writing the formula. What's the objective function? So objective function, we need to multiply Cij's by Xij's and give the sum of them. So it's going to be again, as usual, this is exactly the same as transportation, sum product of the cost coefficients and decision variables and so on. Since they are all zeros, then this sum also is 0 for now. For plant A, I have a constraint that the sum for x11, x12, x13, x14 must be equal to 1. So here I need to write equal sum of these values must be equal to whatever I have here. However, they are all ones. I can just write directly 1. And since the same thing happens for the other rows, then we can select this 3. I can even delete, I can even delete these values to show that if you write one of them, then you can copy for the others. Now I wrote a formula here, another one here, and we want this formula for xij not to move down. On purpose I do once to show that you should lock the cells for the decision variables. Now if I look at here, I can see that up to now, so we moved from this row to the other row, it's correct, and right hand side also from that to this one. So in each row we are considering the xij in that row, and then we are moving down, so the row number is not locked to be able to move down for the formula. So we go up to the end. For the column also the same. In the first column for first city I have the sum of these values must be equal to, again, add value, that blue one. Again, I can select them, move to the right. Since they are in the columns, these values also appear in the column. The column number is not, the column name is not fixed or locked, then it moves forward and gives us the query. For example, this one should be the third column, that's all. Now, what are these? We are going to consider this one also, solving with the solver. Now, if I run the solver, and again I reset to start from beginning. So where is the objective value is going to be kept here. Type of the problem is minimization. Decision variable is considered to be here. And we add the constraints. All these rows should have sum equal to 1. And all the columns must have, again, sum equal to these ones. And we have one more, and that is the difference between transportation and assignment. We should select all these cells and say they are all binary. They are all zeros or ones. And okay, now again we use simplex, select the second one, and solve. We get the same as we had previously. So the problem was balanced. We didn't need the dummy row or column. The difference between transportation and this one, just we mentioned these values are all ones, and at the end you need to add one more constraint. Now I continue by the next example, and also we will solve next example by another method, which is efficient method for the transportation problem, and it's called Hungarian algorithm. Now in the next exercise we have similar question, but this time instead of minimizing the cost, we are minimizing the distance. Almost the same thing. So between cities, or between a place that we have the trucks and different cities, we have distances. Then we want to select or assign each truck to one of those vacant spaces in a way that we have the shortest distance or the minimum distance. In total, we want to have the minimum distance after this assignment. Now, A, B, C, D are some vacant spaces. 1, 2, 3, 4 are 4 trucks. And these are the distance between them. Now we want to send these trucks to those destinations by minimizing the total sum for the distances. Again, we brought all the information inside this matrix. These are the cost coefficients, but in this case, the cost coefficients means distances. The problem is balanced, the sum of these values. You can see this means the sum for this column, and that means the sum for this. For the rows and the columns are the same. Problem balanced, no need for dummy row or column. If we need, we can add, and in some case you may need more than one dummy row or dummy column, because in each row I have only a 1. Then if the number of rows is, for example, 2 times more than or 2 more than the number of columns, then I need 2 dummy columns, each by the value 1. Then I can continue by the cost coefficients all equal to 0 for the dummy columns and solve the problem. Now the problem balance, these are the decision variables. Again, we do it again. But mostly in this part, in this example, we want to show how you can solve directly without the solver or without converting to a linear programming with binary conditions. Now, so these are the decision variables, the places we should save. Objective is sum product of cost coefficients and decision variables. First constraint is the sum for the first row, which must be equal to, this is just equal to that value, and I copy it for the other rows. For the columns also the same, equal sum for the values here, xij's, to be equal to this value, and so this is for the trucks. Each truck is going to be assigned only to one vacant place, and again xij 0 or 1. Now start to solve. So I don't do these things again because once we did in the previous example, and we see that the objective has the minimum value of 17. When we decide to send truck 3 to the vacant space A, this one means that truck 2 will go to vacant space B, truck 1 to C, and truck 4 to D. But based on the cost that we have there, we need to add those costs, give this 17 as total cost, or here total distance. Now, I wrote the same cost coefficients here to explain how Hungarian algorithm works. So the method is named after 2 Hungarian mathematicians. In some textbook, you may see the name of this algorithm as Egervary algorithm. So Dénes Koenig and Jenő Egervary, the 2 Hungarian mathematicians who did some research related to this topic, but later Monkress introduced this algorithm, and we may see this algorithm by his name also, but he himself named the method in the honor of these Hungarian mathematicians as Hungarian algorithm. Now, what is the Hungarian algorithm and how it works? We want to find some values like this 3 there, or this 2 here, maybe here another 4, another value in this, adding them up to get the minimum cost in a way that each row, each column, we have only one selected cell, which is the assignment of, or assigning the row to the column. But we do this calculation. If I subtract a value from a row, what's going to happen in the total cost? Since from each row we are going to select only one cell, then the total cost will decrease by that 3. It means that I can subtract, for example here, 3 from everything or every entries in the first row, and at the final solution, add that 3 to the total solution. Or the solution will not change, but the optimum value will change by 3. Why do we do this? Because we want to create some zeros and select only the zeros. We are doing this calculation of these subtractions and creating some still non-negative values if I have some non-negative values inside these cells and try to select some cells or some xij's as a final solution, then it cannot be less than 0 because we have all non-negative values. We are adding those non-negative values. But if you can get this total sum equal to 0, so for sure it's the optimum solution. Now, what do? We select the minimum in each row and subtract from all the entries in that row. And at the end, I can add this tree to the total cost. And the second row, the same. The minimum in the second row is 2, then I wrote here just minimum of this. Now after finding this minimums, what do I do in the next row? In the first row, I subtract each cell's value, subtract the minimum value of that row from each cell's value. And I can copy to the row and then also to the column. At the same time, by one equation, we can complete the next matrix. Now, if I have zeros in all columns, then no need for this step. But in the second step, the same thing. If we subtract something from a column, then in total cost, or then the optimum solution, since we are going to have only one cell selected in this column, then the total cost will decrease by that value. Then I add the same to the total cost to give the original value or the exact value for the original problem. Now, if I have zeros as minimum for the columns, then no need to do any calculation. But in this column, I don't have 0, so the minimum is 3. We subtract 3 from all these entries, then they change to 1, 0, 2, 1. The same thing that we can see here. Now, after doing these two steps, we created some zeros. We will try to select one cell in each row and also in each column, only a cell. And if I can select all cells like this with 0 value, then this is the optimum solution. So if we try to select zeros, so it's better to start from row or column with the least number of zeros. For example, in the first column I have 1 0. I may select this cell. And after selecting this cell, then in this row and this column I cannot do anything. Then if I remove this column and this row, in the remaining part I have a 0 here. I can select, let me show it maybe. If I make it by another color, so I'm going to change the color. So I select this cell, this 0. Since this 0 is selected, then I'm going to cross out or maybe change the color of this column and also that row. Now, for the remaining part, in the second column I have a 0. I can select that one. If I select that 0, we use another color. I select this cell. Since I selected this cell, I need to cross out this row and this column. Then I need to cross out this row and also this column. Now for the remaining part, in the last column, there is no 0 to be selected. It means that at this point we cannot give the final solution. Or if this thing does not happen or it's not possible, it means that if you want to cross out the zeros by some horizontal or vertical lines, for sure we can cross out by n vertical or n horizontal if n is the dimension of the matrix. Here we have 4 by 4 matrix. By 4 vertical lines I can cross out all elements, so for sure all zeros. But if you can cross out by less than 4, like this, we crossed out all zeros by 3 lines, vertical or horizontal. It means that you cannot select all zeros and give the final solution in this stage. Now, after crossing out all zeros like this, we look at the uncrossed cells. In the uncrossed cells, let me change the value of this one also, the color of this. So look at these blue cells which are not crossed out. We find the minimum between them and subtract that from all the uncrossed and add to the double crossed. Why do we do this, or why it works? I will explain right now, and this is the basic or important part of the algorithm, because here subtracting from rows or columns are almost clear, but here I select 1, for example, and I want to subtract 1 in this column and that column. So I'm subtracting 1 in 2 columns. If I subtract 1 in 2 columns, the total cost will be decreased by 2, because 2 times I subtracted once. Now, if I add with the crossed row, with the entries in the crossed row, again, we need to subtract one of those ones, because we add 2, then we need to subtract 1. So in total, we are going to decrease the total sum by 1 by the system. But if I subtract from uncrossed rows and add the crossed rows, so this 0 once we will add, because it is in the uncrossed column, in this column we are adding, so this 0 becomes 1, subtracting, sorry, becomes -1, and adding in the crossed row, then it's going to come back to the original value. So the entries which are crossed ones will not change. Entries which are double crossed will increase by 1, because this column is crossed, so we are not subtracting, but as a row it is crossed, we are adding. So the problem is like, or the procedure is like this: subtract in the minimum between the uncrossed values. After selecting that, what's the minimum? Here I wrote minimum is 1 between this 1, 2, 1, 2, and that 5. Now I subtract this one from these 2 columns and add to the crossed row. Or we can say another way: we can subtract from these 3 rows and add to the columns. So if you are subtracting, it seems that you are subtracting from everything, but if you are adding to the crossed. Now if you subtract from rows, then you are going to add to the crossed columns. Or if you are subtracting from columns, we selected second column and fourth column to subtract that 1 from all of them. After subtracting from these 2 columns, then you just add to the crossed row. So those cells which are only one time crossed will not change, but double cross will increase by 1. Now you can see that this 6 will change to 7, that 3 to this 4. The cells that we had as cells with one line or one crossed only once, they didn't change, and we created some more zeros. Now by the new matrix, you can see that there is possibility to select zeros in all rows and columns. In the first row, I have only 1 0 selected. In second row, only a 1. Third row, only a 1 cell with a 0 value. Fourth row, the same. In each column also, I selected the same way. Now, how do we start to do this? Again, we start from a row or a column with the minimum number of zeros. In the first column, I have only 1 0, then I have to select this one. In the second column, we have 2 zeros. I have the option to select this cell or that cell. So in this solution, I selected fourth row, second column, but in the other solution I selected second row, second column. So we can say that these are going to be multiple solutions. We have more than one solution but with the same optimum value. Now this must be selected in the first column because we have no other option, no other choice. In the second column we have 2 zeros each time I select one. Now if I select this one, second column, fourth row, what can I do for the other columns? For the other columns, again, I have two options here. I can select this zero in first row, and for the last column I have to select this zero because the other zeros cannot be, this zero cannot be selected because I have a zero in this row, that one there's another zero in this row, so this is the solution. How about if I select this zero and that one? So for sure I cannot select this zero because it's already we have another selected cell in this row, so there's no more choice. If I continue by this two, we have only one solution. But if I continue other way, so this was selected at the first stage, in the second instead of this zero, now we'll continue by that zero. If I continue by this zero, then in the second column I have two zeros, I can select either one. Selecting the top one, then we have another choice for the last column. Selecting the bottom one, again we have another choice for the bottom. So what are these values here? These are exactly the sum of cost coefficients for these selected cells from original problem. We can say that these values. Cool. What is this Z17? Look, there's 3 here and that one there. There's 3 here and the 1 there. So again the sum is 17. And this one, we have these two values here and those two selected cells here. These two and these two. Cool. Now how can I get the same Z star without continuing? Just I don't want to give the solution, I want to give only the optimum value. So considering the Hungarian algorithm, we see that subtracting this 3 here, at the end we had to add this to the optimum value. Since at the end we have all zeros, then I need to add this 3, so I can write equal sum of these values and these values that we selected, and once we want to subtract here one from rows and or uncrossed cells and add to the double cross, we had another one here. I just selected one here because I don't know where I put that one. I guess it was below this, but I select this one for now. I get the same 17. So it shows that what's happening in each step by subtracting these values, and finally if I consider this solution, so I have 0, 0, 0, 0. So the total cost is not 0 because we changed the problem. How we did that changes by subtracting in a row or in a column. If you subtract in a row, at the end you need to add the same value to the total sum. If you subtract anything from a column, the same thing. Here also we see that if I subtract from rows and add to crossed columns, it's going to be 3 minus 2, again is this a 1. If I subtract from columns, I'm subtracting twice, 2 times 1, then it is 2, and adding in a crossed row, again it is only a 1. So subtracting 2 times and adding once, or subtracting 3 times and adding twice gives us the same value. So whatever the uncrossed, the minimum among the uncrossed is going to be added to the sum of these values. After doing this summation or this step at the third stage, we may need to continue. It means that after adding or creating this many zeros, still we may not have enough zeros to be able to select the solution with optimum value 0 in that changed problem, then you need to do this step again. For example, after doing this again, I can cluster out by 3 vertical or horizontal lines. We should do this step up until we have enough number of zeros to be selected and give the final solution. So the problem has multiple solutions, and if you want to solve by Hungarian algorithm, for sure you need to give all of them. These are the possible solutions. So we studied the difference between transportation and assignment, and also we saw how they were similar to each other. The methods of solving with solver, they were almost the same, just you need to add one more binary constraints in the assignment problem. And as we mentioned previously in the previous video, I will explain similar method, not similar to this, I mean another method that we can solve transportation problem also directly without converting them to linear programming like this, and then solving by simplex method. That's all for this video.